V for the system. Could just say V?
No, this is room G. You're in the right room. You're in the right room. Good.
So where does
You can start right now.
right now? Okay. Welcome back. So yeah, the first talk of this session is on local simultaneous state discrimination, characterization, and application to uncloneable cryptography. Yeah. So yeah, please start.
Thank you. Thank you everyone for attending my talk. Today I'm talking about a variant of distributed state discrimination and its application to cryptography. This is a joint work with Marius Ozols, Christian Majenz, and Christian Schaffner, my postdoc supervisor. We have two available talks, papers on arXiv, and there is a longer version of this talk available on YouTube if you are interested. I start with the definition of quantum state discrimination. The formalism is as follows. A referee prepares a classical value x according to some distribution px, prepares some state rho ax depending on the classical value, and send it to some party, we call it Alice. And Alice performs some measurement described by a POVM mx to find the value of x. And you can write down the expression for the probability that x is equal to x hat. This is the simple expression. And this problem has many applications in crypto, in quantum information theory, and quantum computing. A natural extension of this problem is to multi-party state discrimination or distributed state discrimination. Here, in the simplest version, the referee prepares a biparty state and gives each part to one party, and the parties collaborate in some way to estimate the value of x. And we can have different models of collaboration. One well-studied model is so-called LOCC. The parties can perform local operation and classical communication, or there are other studied models. For example, they can perform a local measurement and they can perform a joint post-processing on their outputs to find the value of x. And it has been shown that the probability of correctly guessing can be significantly less than the case when one party received the whole bipartite state. And this observation has many applications in, for example, data hiding. Now the problem that we studied in this work is, we call it local simultaneous state discrimination, or the abbreviation LSSD. A referee here samples some classical value x according to some distribution again, and it prepares a bipartite state rho x AB, and it gives each part again to two parties, Alice and Bob, and Alice performs some POVM, Bob performs another POVM, each one find estimate of the classical value, and Alice and Bob win if and only if they both correctly guess the value of x. We think that this is very natural problem to study. This is a fundamental problem in quantum information theory, and also it has application in quantum cryptography that I will talk about at the end of this presentation. Now I have a few remarks about the model. First, there is no communication allowed between Alice and Bob. This is very different from the case that they can have some classical communication. For example, if they can communicate, if Alice finds the value of x, then it can send it to Bob. But here they should separately find the value of x. However, we allow them to share some resources. For example, they can share the quantum or classical state sigma A prime B prime. This can be classical or quantum state. And if you fix everything, the distribution, the states, the shared resources, the measurement that they can perform, then again, you can write the optimal probability of the probability of winning. And we want to somehow optimize this probability of winning. But this is a linear expression in terms of the state sigma A prime B prime. And you can show that this state should be somehow extreme. And so it should be entangled, the separable state, because they're not extreme state, they cannot achieve the maximum. Now we define two quantities for a problem. We call it classical value and the quantum value. The classical value is the optimal probability of winning over all the strategies that the parties cannot share any resources. And we call it classical because I argued that if they share some classical state, it doesn't help. So this is the optimal probability of winning using only classical resources. And we also define the quantum value, which is the optimization over all shared quantum states and measurement on the joint states of the received state and what they shared before. And there are two natural questions here. First, what is the relation between these two quantities? In other words, whether these quantities are always equal, or there are some cases that there can be some gap between these two quantities, and also what is the computational complexity of finding the optimal value. To answer this question, we considered a special case of this problem where everything is classical. It is easier to study this problem. Here, the referee samples 3 random variables X, A, and B according to some distribution. It sends A to Alice, B to Bob, and Alice and Bob, they want to find the value of X. To simplify the expression for the classical value and the quantum value of this problem, when everything is classical, they cannot share any quantum state, then it's a completely classical problem. And Alice, for example, receives some classical input and it outputs some classical value. So it can be represented by some classical function, for example, F. And we can write down the optimal probability of winning in terms of a maximization over the function for Alice, F, and a function for Bob, we call it G. And we can write down the probability of winning for fixed functions F and G. For a quantum case, it's a bit different. They can share some quantum state. We call it again sigma A prime B prime. And based on their input, the classical input, they can perform some POVM on their shared resources. And again, we can write down the quantum value in this case is optimization over all shared states and all measurements based on their input. And you can simplify this expression a little bit by using some properties of operator norms. Here, there is no optimization over the quantum states, but it's somehow hidden in the optimization in the definition of the operator norm, but it looks a bit simpler. Now, the classical problems might look very simple, but they can be still interesting. I give 2 examples here of completely classical problems. The first example, we have a classical bit X, and we send it to 2 parties, Alice and Bob, but the bit can independently get flipped with some probability alpha. Now, if you look at the classical value as a function of alpha, if alpha is small, then with high probability they get the correct bit, and it's good to output what they receive. And the probability of winning would be 1 minus alpha square in this case. But when alpha is greater than this value 1 minus 1 over square root of 2, then this 1 minus alpha square would be less than 1/2, and they can always achieve 1/2 by outputting a fixed value, for example, 0 or 1. So in this case, we have actually 2 regimes. The first regime where the noise is small, we have low noise regime. And in this case, it's good for them to increase their precision and they output what they receive. And we have another regime that the noise is high and it's good for them to increase the coordination. And they just output a fixed value. And this is not their local optimal strategy, but together it's the best thing that they can do. Now, another example is motivated by this question. Suppose that X is a Bernoulli 1/2 random variable, and A and B are 2 random variables which are independent. Now, the question is that whether the classical value of this problem is equal to 1/2. And why I'm asking this question? Because if from A and B you can simultaneously guess X, it shows some kind of correlation between A and B. At least it was my intuition first I thought about this problem. But we actually find examples that here A and B are independent, but and X is Bernoulli 1/2, but they can find the value of X with some non-trivial probability. So it's although A and B are not correlated, their correlation with X can be used to estimate X with some non-trivial probability. Now, we can ask what is the quantum value of these two examples. I will answer this question later in my presentation. Before that, I need to define something called a no signaling strategy. First, note that any classical or quantum strategy can be completely characterized by this distribution Qx a hat, xp hat, and given A and B. So given some inputs, what is the probability that Alice and Bob output something? And we call a class, we define a class of this kind of distribution in this way. If you look at the marginal distribution of X A hat given A and B, it shouldn't depend on B. And we call it no signaling because it intuitively makes sense. If Alice and Bob cannot communicate, then Alice's output shouldn't depend on Bob's input. And we can also define the no signaling value as the maximum probability of winning over all these no signaling strategies. We denote it by this omega ns. And why do we care about these strategies? First, they give us an upper bound on the quantum value because you can check that any quantum strategy is actually a no signaling strategy. And also, it's easy to compute this no signaling value because all the constraints are linear. It's a linear programming, and you can solve it in an efficient way. Here is a list of our result. Our first result is that there exists some example that all these three quantities are different. So if you have different resources for that Alice and Bob can share, you can get different precision of the estimation in this problem. Our next result is that if X, A, and B are all binary, then there is no gap. All these three quantities are equal. And it answers my question in the previous slide that for our example, everything were binary. So in those examples, the quantum value is actually called the classical value, and there's no gain in sharing some entanglement. And finally, you can extend this LSST problem to more than two parties. You can have, for example, three parties. And if you have three parties LSST, we prove that it's NP hard to find the optimal value. Here's the example that shows the separation between these values. It's not that complicated example, but this is not the first example that you look at the beginning also. First, note that X can take three values, so it doesn't contradict our other result that if everything is binary, you don't have a separation. And for this particular example, we were able to find all these three values. Actually, the classical and no signaling values are not that difficult to compute. We have relatively simple expression to find them, but finding the quantum value is not straightforward to compute at all. It's a maximization over all Hilbert spaces for Alice and Bob, and over these two Hilbert spaces, you can have any bipartite state, and then you have optimization over the measurements. It's very complicated optimization. But for this example, we were able to find analytically what is the optimal value. Even numerically, it's not trivial to find this optimization. And this is maybe the most non-trivial and technical part of our work. And this is mainly due to Maurice. He managed to do a very complicated optimization trick to find this value. Next, I will talk a little bit about how we prove the NP hardness of finding the optimal value for three-party LSST. I need to define first hypergraphs. A hypergraph is a pair of vertex set and hyperedge set. Each hyperedge is a subset of vertices. Instead of connecting two vertices, it's connecting multiple vertices. And we also define R-partite hypergraphs. The definition is as follows. We can partition the vertices into R parts such that each hyperedge intersects with each part exactly in one vertex. And here's an example of hypergraph. I took it from Wikipedia, and here is an example of tripartite graph. Each color represents one part. And graphs are a special case of hypergraphs with hyperedge exactly size 2. Next, I need to define matchings for hypergraphs. A matching is a collection of hyperedges that are mutually disjoint. This is consistent with the definition of matching in regular graphs. And also the fractional matching is a function from hyperedges to numbers between 0 and 1, such that if you look at each vertex, the hyperedges that contain that particular vertex, the sum of that function is less than 1. And this is a famous example of difference between the matching and fractional matching, that they can be different for the cycle of length 5. And it is known that finding the maximum matching for tripartite hypergraphs is NP-hard. For bipartite graph, there are efficient algorithms, but for tripartite, it's not. Now, I want to reduce this problem of finding matching in tripartite graph to LSST. Given any R-partite graph, hypergraph, I define an LSST in the following way. I sample one hyperedge at random. It has exactly R vertices. I give one vertex to each party, and each party should, based on the vertex that it receives, it should guess what is the edge that I sampled. And for this particular problem, we can characterize the classical value exactly. It's equal to the size of the maximum matching divided by the number of edges. And the no signaling, we could upper bound it by the size of the maximum fractional matching divided by the number of hyperedges. And this theorem has 3 consequences. First, it shows that finding the optimal classical value for tripartite LSST is NP-hard, because if you can solve it, you can solve the tripartite matching problem. And if P is not equal to NP, there exists a tripartite hypergraph that the classical value is different from no signaling value, because for no signaling, you can write a linear program and you can find it in polynomial time, and the classical value is NP-hard. If they're always equal, then P is equal to NP. And finally, for bipartite graph, all these 3 quantities are equal, because the maximum fractional matching for bipartite graph is always equal to the maximum matching for bipartite graphs. Finally, I speak about the application of this LSST to cryptography. Suppose you have a classical message M, and you have a classical key K, and you encode this message using this key into a quantum ciphertext. And then you have 3 adversaries, Eve, Bob, and Charlie. In the first step, Eve receives the ciphertext. It doesn't know the value of the key, and it copies the ciphertext into 2 registers and gives each register to one of the other adversaries, Bob and Charlie. Then Bob and Charlie have the value of the key, and they receive some quantum register, and they perform some measurement to decode the message. And they win if they all decode the message correctly. Now, we were able to lower bound the probability of winning for the adversaries by this quantity. Ideally, we want to make sure that the probability of winning is very close to 1/2, but we show that there is always some gaps. And for example, if the ciphertexts are pure in this setting, then the operator norm of this ciphertext is equal to 1, and we show that there is a constant gap between the trivial value and the value that the adversaries can achieve. And this is not a good news for cryptography. But the proof, I just sketch very high level ideas of the proof. We used the following cloner. It somehow distributes the message in a superposition way. There are 2 branches of the superposition. In one branch, the message is completely given to Alice, and in the other to Bob, and in the other branch is completely given to Charlie. And If you suppose that everything is pure, the ciphertexts are pure, then the problem is completely reduced to an LSSD. And for this LSSD, we have to find the classical value. And we were able to lower bound the classical value by 9/16. And this is exactly the same as the value that we have in the theorem if the states are pure. Then this the numerator is 1, and we get this 9/16. Now, I conclude my talk. In this work, we formulated the LSSD problem. We showed that entanglement can help us to increase the probability of winning in this problem. And we showed that finding the optimal value for three-party LSSD is NP-hard. One obvious question is, what is the computational complexity for two-party LSSD? We don't have answer for that question. And we can also find quantum examples that entanglement can help. The examples that we have here is completely classical. Is there any quantum example? And we can also relate this classical or quantum value to some information theoretic quantities. For example, in Fano inequality, we are relating the probability of guessing for single party to conditional entropy. Can we have similar inequality for LSSD? Yep, that's it. Thank you for your attention. I would be happy to answer any questions.
Yeah, so questions?
Hi. Thank you for the interesting talk. So with the quantum bound, you didn't talk about the proof you gave, but could you not use NPA to get a kind of simple upper bound on the quantum value, and that would prove the gap between quantum and non-signaling, or did I miss something?
That's a very interesting question. Yeah, we try to find the first level of NPA hierarchy, and we get a separation between no signaling and quantum value, but we couldn't get the optimal value for the quantum. We have to use more complicated techniques to find the exact value of the quantum value.
Great. And maybe related to this is, I was just trying to, is there a link to non-locality here, to non-local games? Because it looks like, at least in this simple case where the state, everything was classical in your example, it looks somehow like a kind of an interesting parallel situation.
It doesn't exactly fall into that category because the distribution of A and B depend on some other classical random variable. In the non-local game, the distribution of the inputs is fixed. Here, the distribution depends on X, and X is random also. Okay. But we can, there are some versions of non-local games that we can formulate this problem as that.
And just one final quick question. Have you thought about using it to quantify the entanglement necessary between Alice and Bob? Like so if you put a bound on the amount of entanglement they share, you might be able to bound the score. I don't know, this might be an interesting way of doing kind of device independent entanglement quantification.
That's I don't know answer for the particular example. Actually, we need only one. It's not EPR pair actually, but the dimension are 2. I don't know if we put some bounds on the entanglement, how it changed the problem. That's an interesting question to explore.
Thank you very much.
Thank you.
Thanks for the very nice talk. So yeah, so like a few years ago, we had like a paper on that, like same spirit, but then you have this kind of an XOR game instead of this LSSD game. So yeah, I guess if you can relate the two, or it's not obvious, right?
You can view it the XOR games as when both parties are wrong, you also win. Yeah, it's exactly. A bit different, and so we couldn't able to use all the results for XOR games here because we have nicer expression for XOR games. We cannot use them here completely. Yeah.
Right. And you have any idea on what like the simplest example of quantum advantage would look like?
I don't know. We try to numerically search for some quantum examples, but
So like, because the standard one would be, say, antisymmetric and symmetric normalized projectors, right? So like 3 Malvern states, you have to discriminate them. Maybe even a single EBIT could help.
Yeah, that's, I haven't thought about that examples, but yeah, that's a natural example to think about. Yeah.
Right, thanks.
Thank you.